Somewhere, far beyond the reach of our naked eyes, there exists a ghost in the cosmos, a galaxy so strange that it rewrites the very rules we thought govern the universe. Imagine looking into the night sky and realizing that right there, hiding in plain sight, is an enormous galaxy, but one that is almost entirely invisible. Not invisible because it's small, not invisible because it's hiding behind something else, but invisible because the stuff that makes it up, its very essence, refuses to interact with light at all. This is no ordinary cosmic curiosity. This is a world built almost entirely from dark matter, the elusive, mysterious substance that astronomers know is out there but cannot touch, taste, smell, or see. And yet, somehow, it holds galaxies together, bends the path of light, and shapes the grand architecture of the universe. But before we continue, subscribe to the channel and like the video. That's where the mystery begins, a story about a galaxy that shouldn't be this way, a place where 99% of everything is hidden in darkness. You see, when we look at most galaxies, even if they're rich in dark matter, we can still see their stars, their gas clouds, their spiral arms, or their glowing cores. But this galaxy, which you could fit next to our Milky Way in terms of size, stares back at us like a whisper from another reality. A faint smudge in the cosmic deep that says, "I am here, but you'll never truly see me." It's a chilling thought, really. A reminder that even in the age of powerful telescopes and high-definition images of galaxies billions of light-years away, the universe still keeps secrets so profound that they can hide in places we've been looking at for decades. Dragonfly 44 is one such secret, an astronomical riddle wrapped in the cold, invisible embrace of dark matter. It's not just that it's made mostly of the stuff, it's that it's almost entirely made of it. Before its discovery, astronomers suspected that galaxies dominated by dark matter existed, but to stumble upon one of this magnitude and peculiarity was like finding a skyscraper in the middle of a desert and realizing it was built out of glass so clear you could hardly see it. To the human eye, it would almost be as though it wasn't there at all, and that's exactly the kind of deception the cosmos is good at. When we first learned of this galaxy, it forced scientists to rethink how galaxies form, how dark matter behaves, and whether our models of the universe are missing key pieces of the puzzle. This isn't just a curiosity for specialists, it's a piece of evidence in the ongoing investigation into one of the greatest scientific mysteries of all time. And as with all good mysteries, the more we learned, the stranger it became. Now that the stage has been set and the intrigue is thick in the air, it's time to meet the star of our cosmic drama, a galaxy with a name that sounds almost delicate, almost fragile, Dragonfly 44. The name itself has a poetic quality, as though it could belong to a rare butterfly in a collector's case, yet the reality is far more epic and alien. Dragonfly 44 is no fragile thing. It is massive, sprawling across the darkness of space, and yet it is wrapped in a cloak of near invisibility. This is the paradox at the heart of the story, something so big, yet so faint, that it almost managed to slip under humanity's astronomical radar entirely. The dragonfly part of the name isn't a whimsical metaphor invented after the fact, it's tied to the very instrument that brought it to our attention, the Dragonfly telephoto array. This is a rather unique telescope system designed for a singular purpose, spotting extremely faint objects in the universe, ones so diffuse and dim that traditional telescopes often fail to notice them. The 44 in its name is simpler. Dragonfly 44 was the 44th such object catalogued during a particular survey. That might sound plain, but within the field of astronomy, these catalogue numbers become like badges of honor for rare and unusual finds. And rare is an understatement here. While thousands of galaxies have been catalogued and studied, Dragonfly 44 stands in a category of its own. It is an ultra-diffuse galaxy, a type of galaxy with stars so spread out and so dimly lit that it's almost like the cosmic equivalent of fog. If you think of a normal spiral galaxy like the Milky Way as a bustling city full of bright skyscrapers, glowing windows, and streets bustling with lights, then Dragonfly 44 is a ghost town in the dead of night, with only a few dim street lamps flickering here and there, the rest cloaked in darkness. But the real twist in its identity isn't just its faintness, it's the realization of what lies beneath its ghostly face. In normal galaxies, the stars, planets, and glowing gas clouds make up a healthy fraction of the total mass. Dark matter still dominates, but it shares the cosmic stage with visible matter. In Dragonfly 44, however, visible matter is almost an afterthought. If you were to strip away the invisible stuff and leave only the visible components behind, you'd be left with a pitiful sprinkling of stars compared to a galaxy its size. That's why astronomers were both fascinated and perplexed when they realized that this faint smudge they had spotted was, in terms of gravitational heft, almost the size of the Milky Way. Think about that. Here is a galaxy with almost the same overall mass as ours, yet you could stand in it and possibly drift for thousands of light-years before coming across another star. The empty spaces between those stars would be filled almost entirely with nothing you could see. But it wouldn't be true nothing. It would be dark matter, unseen, undetectable through conventional means, yet making its presence known by the way it tugs gravitationally on everything around it. The name Dragonfly 44 has now become synonymous with one of the most extreme examples of a dark matter-dominated galaxy. Whenever scientists or science communicators bring it up, it's not just in passing. It's in hushed tones or with that excited edge in their voice that says, "You're not going to believe this one." And indeed, when you first hear the numbers, 99% of its mass in dark matter, it does sound unbelievable, almost like science fiction. And yet, the universe is under no obligation to make sense to us. In a way, the name Dragonfly is fitting in more than just the technical sense. Dragonflies in nature have wings so delicate and transparent they can seem almost invisible at a distance, yet they are strong flyers, capable of rapid, agile movement. In much the same way, Dragonfly 44 is almost transparent in the vastness of space, but underneath that faint exterior lies a gravitational backbone of immense strength, one forged not of starlight, but of unseen matter. Astronomers love giving poetic spins to their discoveries, and even though Dragonfly 44 is just one entry in a numerical list, the combination of its delicate name and its monstrous reality gives it an aura. It feels more like a character than just an object. A character in a mystery we have only just begun to read, with most of its pages still shrouded in darkness. When it was first presented to the astronomical community, it didn't immediately become a household name. After all, it wasn't flashy, like a newly discovered supernova or an exoplanet in the habitable zone. But in the years since, its fame has quietly grown, especially among those fascinated by the concept of dark matter. The more you look at Dragonfly 44, the more it becomes a symbol for the unseen universe, a reminder that the visible cosmos is just the tip of the iceberg. And perhaps this is the most poetic part of all, in a universe where we often define galaxies by their visible beauty, their swirls, their arms, their blazing cores. Dragonfly 44 earns its place in the pantheon by hiding almost everything from view. It's the cosmic equivalent of a whisper so faint that you need specialized equipment to even know it's there. And once you've heard it, you can't stop thinking about it. If we want to truly understand Dragonfly 44, we first have to situate it within the cosmic map, because location, as any real estate agent or astrophysicist will tell you, matters. Dragonfly 44 is not floating alone in some empty pocket of the universe. Instead, it resides in one of the most crowded, gravitationally powerful neighborhoods we know, the Coma Cluster. The Coma Cluster is a massive gathering of galaxies, a gravitational city with over 1,000 confirmed galactic residents and perhaps many more smaller, fainter ones. If you could somehow stand far outside the cluster and look in, you would see a sprawling cloud of light, hundreds upon hundreds of galaxies packed into a space only a few million light-years across, bound together by their mutual gravitational pull. This is not some gentle gathering. The Coma Cluster is the product of billions of years of gravitational interactions, collisions, mergers, and galactic cannibalism. It is a place where galaxies are constantly tugged, twisted, and sometimes ripped apart by the intense gravity of their neighbors. Now, here's the staggering part. Dragonfly 44 sits about 330 million light-years from Earth, nestled inside this cosmic metropolis. That number is so large it's almost meaningless in day-to-day human terms. Let's break it down. Light, which moves at nearly 300,000 kilometers per second, takes 330 million years to reach us from Dragonfly 44. That means when we look at it, we're seeing it not as it is today, but as it was back when early life on Earth was still adapting to life on land and the first mammals were over 200 million years from evolving. It's a time capsule from deep cosmic history. In astronomical geography, the Coma Cluster belongs to a larger structure known as the Coma Supercluster, part of an even vaster network of galaxy clusters and filaments making up the cosmic web. This web is the large-scale skeleton of the universe, long tendrils of galaxies and dark matter connecting like neural pathways across unimaginable distances. Within this web, the Coma Cluster stands out as one of the most massive and densely populated galaxy clusters in the local universe. For Dragonfly 44, being in such an environment is a double-edged sword. On one hand, the cluster's immense gravitational field keeps it bound within the group. On the other hand, this crowded environment likely influenced its evolution, or lack thereof. Clusters like Coma are known to strip gas from galaxies that pass through them, a process called ram pressure stripping. Without gas, a galaxy cannot form new stars. This may explain why Dragonfly 44 has so few stars compared to its total mass. The Coma Cluster might have robbed it of the raw material it needed to light up the night. The environment also plays into the mystery of its dark matter content. In a place like the Coma Cluster, galaxies are moving at incredible speeds, and gravitational interactions happen often. Some scientists speculate that these interactions can alter a galaxy's distribution of matter, possibly leaving behind a dark matter-rich core after most of the stars are stripped away. Others wonder if Dragonfly 44 might be a failed galaxy, one that had the dark matter halo necessary to become a Milky Way-sized system but never got the star formation it needed to shine. If we could somehow fly to the Coma Cluster and observe it from the inside, Dragonfly 44 would be one of the most ghostly sights in the neighborhood. Imagine a galactic city at night, where most of the residents' lights are blazing, spirals glowing with starbirth regions, giant elliptical galaxies shimmering with the light of trillions of old stars. And then, in the midst of all that brilliance, a faint, barely visible shadow of a galaxy drifting quietly among the others. That's Dragonfly 44, an almost invisible resident in one of the universe's busiest neighborhoods. It's worth noting that the Coma Cluster itself is also incredibly important for dark matter studies. Long before Dragonfly 44's discovery, the Coma Cluster was one of the first places astronomers realized something was wrong with the visible matter count. Back in the 1930s, Swiss astronomer Fritz Zwicky studied the motions of galaxies in the Coma Cluster and concluded that they were moving far too fast to be held together by the gravity of their visible stars alone. He coined the term Dunkelmaterie, dark matter, to describe the missing mass. In a way, the Coma Cluster is the birthplace of the modern dark matter concept. And now, decades later, it's also the home of one of the most extreme dark matter galaxies ever found. This almost poetic coincidence, that a galaxy like Dragonfly 44 would be found in the same cluster where the concept of dark matter first emerged, adds an extra layer of intrigue to its story. It's as if the Coma Cluster has been keeping this secret for us all along, waiting until our technology advanced enough to notice. So when you picture Dragonfly 44, don't think of it as an isolated curiosity. Think of it as part of a colossal, bustling space city, one where the biggest, brightest galaxies dominate the skyline, but where in the shadows, faint and almost forgotten, drift the mysterious, quiet giants like Dragonfly 44. These shadowy residents might just hold the deepest truths about the invisible side of our universe. When you first hear that Dragonfly 44 is roughly the same mass as the Milky Way, it's natural to picture a majestic spiral galaxy, glowing with billions upon billions of stars, full of swirling arms, star clusters, and clouds of nebulae. After all, that's what we think of when we hear Milky Way sized. But here's the shocker: Dragonfly 44 may have similar total mass, yet in terms of actual visible stars, it's a cosmic lightweight, a galaxy that's traded its glitter for near-complete invisibility. Let's start with the Milky Way for reference. Our galaxy is estimated to contain around 200 to 400 billion stars, depending on how you count the faintest and smallest ones. It stretches about 100,000 light-years across, with a bright central bulge, two major spiral arms, and several smaller arms twisting outwards. There are huge regions of active star formation, vast nurseries where massive clouds of gas collapse under gravity to ignite new suns. All of this is embedded in a dark matter halo that provides the extra gravitational glue to hold the structure together. The ratio of dark matter to visible matter in the Milky Way is estimated to be around 85% dark matter, 15% visible matter, meaning that even our luminous home is mostly made of something we can't see, but the visible part is still spectacular. Now, imagine a galaxy the same physical size, with nearly the same total gravitational heft, but with only about 1% of the Milky Way's stars. That's Dragonfly 44. Instead of 200 to 400 billion stars, we're talking maybe just a few billion, scattered sparsely across its vast disk. Where the Milky Way's spiral arms are dense rivers of light, Dragonfly 44's starlight is stretched so thin that, even with the best telescopes, it barely registers above the background glow of the universe. If the Milky Way is a dazzling city skyline lit up from horizon to horizon, Dragonfly 44 is a ghost town where only a few street lamps flicker, separated by enormous gaps of darkness. This is one of the most mind-bending facts about it. In terms of gravitational pull, Dragonfly 44 is in the same league as our galaxy. It's a heavyweight. But in terms of visible content, it's a featherweight. If you could somehow pluck the stars of the Milky Way out of their places and scatter them sparsely across its frame, you might end up with something that looks like Dragonfly 44. But here's the kicker. It isn't just that it lost stars over time. The evidence suggests that it never formed them in great numbers to begin with. The question that naturally follows is, how can two galaxies of the same mass have such dramatically different appearances? This is where dark matter steps into the spotlight. In our Milky Way, visible matter, the stars, planets, and glowing gas clouds, is built atop a vast foundation of dark matter, but the visible matter is still abundant enough to dominate our view. In Dragonfly 44, the dark matter foundation is nearly the entire structure. The luminous component, the stars, is just a faint garnish on top of a massive, invisible gravitational skeleton. Think of it this way. If the Milky Way is like an iceberg where the glowing tip is the stars and the submerged bulk is dark matter, Dragonfly 44 is an iceberg where the tip barely pokes above the water at all. Almost everything about it lies beneath the surface, unseen. Even the sizes match eerily. Observations suggest that Dragonfly 44 has a diameter close to 100,000 light-years, just like the Milky Way. This means if you could stand at one edge of Dragonfly 44 and look across to the other side, the span would be comparable to looking across our own galaxy. But unlike the Milky Way, where your view might be filled with the soft glow of countless stars, the view inside Dragonfly 44 would be unsettlingly empty. You might drift for thousands of light-years without crossing paths with another sun. This stark contrast makes the comparison both fascinating and eerie. Two galaxies, similar in scale, both locked in the same cosmic game of gravitational forces, yet one is a spectacular spiral teeming with starlight and worlds, while the other is an almost invisible behemoth whose mass exists almost entirely in shadow. It's the perfect reminder that the universe's building blocks can take vastly different forms, even when they have similar starting conditions. And this isn't just about aesthetics, it's about physics. The fact that Dragonfly 44 has Milky Way level mass but almost no visible stars tells astronomers something profound. The processes that turn gas into stars either failed spectacularly in this galaxy or were shut down prematurely. It's like seeing two skyscrapers of identical size, but one is fully furnished and lit up while the other is just an empty steel frame standing in the dark. This comparison is one of the reasons Dragonfly 44 is so scientifically valuable. By studying why it's so poor in stars yet rich in dark matter, astronomers can probe the role that dark matter plays in galaxy formation, as well as the environmental factors that might cause such an extreme divergence in appearance between otherwise similar mass galaxies. Here's where Dragonfly 44 stops being just unusual and starts breaking your brain a little, the strange math that underpins its existence. We've already said it. Dragonfly 44 has only about 1% of the stars of the Milky Way. In raw numbers, that means we're talking just a few billion stars compared to our galaxy's hundreds of billions. If you measured only the starlight, Dragonfly 44 would look like a faint, unimpressive smudge in the sky, dwarfed in brightness by the brilliant spiral arms of galaxies like our own. Now here's the kicker. Despite this pathetic star count, its total gravitational mass is nearly the same as the Milky Way's. The Milky Way's mass is estimated at around 1 to 1.5 trillion solar masses, a solar mass being the mass of our Sun. Dragonfly 44 comes in at a very similar ballpark. How? This is where the numbers force you to confront the reality of dark matter in the most dramatic way possible. For most galaxies, visible matter, stars, gas, dust, makes up a significant portion of the total mass, though still far less than dark matter. But in Dragonfly 44, the visible portion is tiny. Imagine a pie chart where 99% of the circle is labeled invisible, and just a razor-thin sliver is labeled stars. That's Dragonfly 44's mass breakdown. Let's do some thought math to drive this home. If you give the Milky Way 1 trillion solar masses total, about 150 billion solar masses are in stars. The rest, roughly 850 billion solar masses, is in dark matter, plus a small fraction in gas and dust. Now give Dragonfly 44 that same 1 trillion solar masses. Only about 1 to 2 billion solar masses are in stars. The rest, a mind-bending 998 billion solar masses, is dark matter. That means if you somehow stripped away all the dark matter from both galaxies and compared the remaining stars, the Milky Way would still weigh more than 100 times as much as Dragonfly 44. And yet, when the dark matter is included, the scale tips evenly. The way we know this is not by weighing galaxies on some giant cosmic scale, tempting as that image is, but by measuring how fast things inside them move. Stars orbit the center of a galaxy under the influence of its gravity. In a galaxy with little mass, stars move relatively slowly because there's not much gravity pulling on them. But if you measure unexpectedly high orbital speeds, speeds that can't be explained by the visible stars alone, it's a clue that there's a huge amount of extra, unseen mass lurking there. When astronomers measured the velocities of stars within Dragonfly 44, the numbers were shocking. They were moving much faster than the faint sprinkling of stars should allow. The math said, there's something massive here, something invisible, and it's making up virtually the entire galaxy. This is the kind of calculation that turns dark matter from a theoretical concept into an unavoidable reality. In the Milky Way, dark matter explains the extra gravity we see but still leaves us with plenty of stars to light up the picture. In Dragonfly 44, dark matter doesn't just explain the numbers, it is the numbers. The stars are so sparse that they barely matter to the galaxy's total mass at all. It's such a bizarre ratio that when the results were first published, some astronomers were skeptical. A 99% dark matter galaxy? Was that even possible? Maybe the measurements were wrong, or the interpretation flawed. But the more data came in, the more it seemed that this ghostly giant wasn't breaking physics. It was just showing us a more extreme example of it than we'd ever seen. The strange math here isn't just a curiosity. It's a neon sign pointing toward how much of the universe is built on scaffolding we can't see. It's one thing to hear that most of the universe's mass is dark matter. It's another to meet a galaxy where that statement is so literal, so absolute, that the stars are basically decorative. If there's one number that defines Dragonfly 44 and makes astronomers' jaws drop, it's this: about 99% of its mass is dark matter. Let's linger on that for a moment. 99%. That means for every single kilogram of ordinary matter, stars, gas, dust, planets, moons, anything you could theoretically touch or see, there are about 99 kilograms of matter that is completely invisible, untouchable, and fundamentally different from anything we're familiar with. In the Milky Way, as in most galaxies, dark matter dominates, but only to the tune of roughly 85%. That's still huge, but it leaves a respectable share for visible matter to show off. That's why our galaxy has glowing spiral arms, a bustling central bulge, and nebulae lighting up the night with new stars being born. In Dragonfly 44, visible matter barely gets invited to the party. The luminous part is so meager that, without dark matter's gravitational pull, it wouldn't even hold together as a galaxy. The few billion stars it has would simply drift apart into space. To really visualize what 99% dark matter looks like, imagine building a giant sculpture. In the Milky Way, you might construct it mostly out of steel, dark matter, but decorate it with bright, colorful glass panels, stars and gas, so that it's still impressive to look at. In Dragonfly 44, the steel framework is almost all there is, towering, massive, and invisible, and you've stuck on only a handful of tiny glass panels here and there. The frame itself is what gives the structure its size and shape. The decorations are almost irrelevant. The number 99% isn't just dramatic, it has deep consequences for astrophysics. It means that Dragonfly 44 is practically a pure laboratory for studying dark matter. In most galaxies, dark matter is mixed in with complicated stellar populations, dust, and gas, all of which emit light and make it tricky to isolate the gravitational effects of the dark matter alone. But here, the visible matter is so minimal that it barely interferes with the measurements. It's as though nature decided to give scientists a clean sample, stripped of distracting noise, so we could study the invisible scaffolding of a galaxy almost directly. And yet, this also makes Dragonfly 44 profoundly mysterious. We know dark matter is there because of its gravity. It bends the orbits of stars, it shapes the galaxy's halo, it makes the whole structure weigh far more than its stars can account for. But we have no idea what dark matter actually is. It doesn't emit light, it doesn't absorb light, it doesn't interact with normal matter except through gravity, as far as we know. It could be made of undiscovered particles, primordial black holes, or something even stranger. The 99% figure just deepens the mystery. Whatever dark matter is, it can completely dominate a galaxy's makeup. This leads to some big, uncomfortable questions. Why does Dragonfly 44 have so little visible matter compared to its dark matter? Did it once have more stars, only to lose them in violent interactions with other galaxies? Or was it born this way, with conditions that prevented large-scale star formation in the first place? And if galaxies like this exist, how many more are hiding out there, practically invisible to our current surveys? Some astronomers have called Dragonfly 44 a failed galaxy, meaning it might have had all the raw dark matter scaffolding to grow into something bright and grand like the Milky Way, but something shut down its star formation early on. That something could have been environmental, like the harsh gravitational tides of the Coma Cluster stripping away gas before it could ignite into stars. Or it could have been more exotic, like unusual properties of its dark matter halo itself. The 99% ratio also adds urgency to dark matter research. If most of the universe's mass is already hidden in this form, and we now find galaxies where it's almost all that exists, then figuring out what it is isn't just an academic puzzle. It's central to understanding the very structure and fate of the cosmos. Dragonfly 44 essentially shouts this fact from the rooftops. Dark matter is not some rare, fringe ingredient, it is the dominant architecture of the universe. It's worth noting that when the 99% figure was first announced, it sounded almost suspiciously high. Astronomers double-checked the data, reran their models, and even debated whether something about the way they were measuring star velocities might be skewing the results. But time and further study have reinforced the conclusion. Whatever Dragonfly 44 is, it is overwhelmingly made of the invisible stuff. And here's the eerie part. From our perspective on Earth, we would never know it by looking. The galaxy's faint starlight is so weak that in a typical deep sky image, it looks like a smudge you might dismiss as a processing artifact. But behind that ghostly veil lies an enormous, invisible gravitational presence, a behemoth in the shadows. Dark matter. Two words that sound like something out of a science fiction novel, yet they represent one of the most stubborn and tantalizing mysteries in all of modern science. At its core, dark matter is a name we've given to, well, something. Something we know is there because of its effects, but which refuses to reveal itself directly. The basic description is deceptively simple. Dark matter is invisible, it does not emit light, absorb light, or reflect light, but it has mass, and therefore it exerts gravity. That gravity is how we know it exists. Wherever dark matter is, it pulls on stars, planets, and even light itself through gravitational lensing. But if you point the most sensitive telescope in existence toward a dark matter-rich region, you'll see nothing. Not a faint glow, not a shadow, not a whisper. It is utterly dark. The fact that it doesn't interact with light is what makes it so hard to detect directly. Our main window into the universe is light, visible light for our eyes, and other wavelengths like infrared, radio, X-ray, and gamma rays for our telescopes. All of astronomy, for most of history, has been about studying what glows. But dark matter ignores all of that. It's like trying to figure out the shape of a room when you can only see the furniture, but there's an invisible, massive elephant in the middle of it, shaping how the furniture is arranged without ever letting you lay eyes on it. So, what is it made of? That's the billion-dollar question, literally, given how much funding goes into research on this topic. The leading theory is that dark matter is made of as-yet undiscovered particles, sometimes called WIMPs, weakly interacting massive particles, or other exotic candidates like actions. These hypothetical particles would barely interact with normal matter except through gravity, which would explain why they've eluded detection so far. Some scientists explore more radical ideas, like the possibility that dark matter could consist of primordial black holes, tiny relics from the early universe. Others even consider modifying the laws of gravity themselves, suggesting that maybe there is no dark matter, just gravity behaving differently at large scales, though this theory struggles to explain the full range of observations. Regardless of what it is, the evidence for something is overwhelming. We first suspected its existence in the 1930s, when astronomer Fritz Zwicky noticed that galaxies in the Coma Cluster, yes, the same cluster where Dragonfly 44 lives, were moving too fast to be held together by their visible mass alone. The math simply didn't add up unless there was a huge amount of unseen mass contributing to the gravitational pull. Later, in the 1970s, astronomer Vera Rubin's work on galaxy rotation curves cemented the case. Stars in the outer regions of galaxies were orbiting much faster than the visible matter could explain. The only logical conclusion was that galaxies are embedded in massive, invisible halos of dark matter. Today, dark matter is a pillar of our cosmological model. We believe it makes up about 27% of the total mass-energy content of the universe. Ordinary matter, the stuff that makes up stars, planets, you, and me, accounts for only about 5%. The rest is something even stranger: dark energy, which drives the accelerated expansion of the universe. This is where Dragonfly 44 becomes such a striking example. Every galaxy we've ever studied seems to have more dark matter than visible matter, but Dragonfly 44 pushes that ratio to an extreme. It's practically a pure dark matter system, a reminder that dark matter isn't just an invisible seasoning sprinkled on top of the visible cosmos, it's the bulk of the structure itself. Without it, galaxies wouldn't hold together, galaxy clusters wouldn't form, and the large-scale cosmic web would never have emerged. In a very real sense, dark matter is the invisible skeleton of the universe, shaping everything we see without ever showing its face. And that's the kicker: dark matter is both absolutely essential and utterly mysterious. We've mapped its effects across the cosmos, yet we can't hold a single particle of it in our hands, can't see it under a microscope, and can't photograph it directly. It's the ultimate case of knowing what it does without knowing what it is. If you were to see Dragonfly 44 through a conventional backyard telescope, even one powerful enough to reveal the spiral arms of the Andromeda Galaxy, you'd likely be disappointed. In fact, you might not see anything at all. That's because Dragonfly 44 has what can only be described as a ghostly look, so faint and diffuse that, for decades, it successfully hid in plain sight. When astronomers describe a galaxy as diffuse, they mean its stars are spread out over such a wide area that their combined light barely rises above the natural glow of the night sky. In astronomical terms, this is called low surface brightness. The Milky Way, by comparison, has bright, concentrated regions, the core, the spiral arms, that make it easy to spot in images. Dragonfly 44's light, on the other hand, is smeared so thinly across such a large area that it's like trying to detect a faint cloud against a backdrop that's already slightly misty. In telescope images, Dragonfly 44 doesn't leap out as a dramatic, structured shape. It has no crisp spiral arms, no bright nucleus, and no vibrant star-forming regions. Instead, it appears as a large, faint oval, a subtle wash of light so delicate it's almost not there. If you weren't specifically looking for it, you could easily mistake it for background noise in the image, a faint smudge caused by a bit of stray light or an imperfection in the camera sensor. This is part of what made its discovery so remarkable. Traditional large telescopes, the kind designed to zoom in on small, bright objects or to capture deep exposures of dazzling galaxies, are actually bad at finding something like Dragonfly 44. They're optimized for sharpness and contrast, but that comes at the cost of sensitivity to broad, diffuse light. It's a bit like trying to find a faint, wide patch of fog using binoculars designed for birdwatching. You can see small details brilliantly, but you'll miss the big, soft patterns. The Dragonfly telephoto array, the telescope that ultimately spotted Dragonfly 44, was designed with exactly this challenge in mind. By combining an array of telephoto lenses with special coatings to reduce internal reflections, it became uniquely suited to detect extremely faint, spread-out galaxies. This is how astronomers were able to see what had been invisible to others, the delicate, ghostly form of Dragonfly 44 lurking in the crowded Coma Cluster. There's also something strangely eerie about its appearance. Because it's so faint and lacks distinct features, it almost looks unfinished. If you were to imagine the Milky Way with most of its stars removed, leaving behind only a bare trace of its original light, you'd get something close to what Dragonfly 44 looks like. It's as if the galaxy began to form but never completed the process, a cosmic sketch left in pencil without the ink and color to bring it to life. This visual emptiness also adds to the sense of scale. When astronomers look at images of Dragonfly 44, they know it's roughly the same size as the Milky Way, but without the dense population of stars, that size is not immediately obvious. Only when you compare it to the background galaxies in the same image do you realize that the faint smear spans a vast region of space, tens of thousands of light-years across. From an observational standpoint, its ghostly look also poses a serious challenge. The low surface brightness means long exposure times are needed to collect enough light to study it in detail. Even then, much of the data comes from measuring the velocities of its few visible stars rather than from imaging its structure. In other words, Dragonfly 44 refuses to make things easy for us. It forces astronomers to use every trick in the book just to coax its faint profile into view. It's this combination, the huge size, the almost total lack of visible matter, and the smudge-like appearance, that makes Dragonfly 44 feel so otherworldly. When you look at the images, you can't help but think, how many more like this are out there, hiding in the cosmic fog, waiting for the right set of eyes to spot them? In astronomy, labels matter, not because scientists like to pigeonhole things for the sake of it, but because naming a category helps us recognize patterns, compare examples, and test theories. Dragonfly 44 has one such label that immediately tells astronomers something about its nature. It's an ultra-diffuse galaxy, often abbreviated as UDG. An ultra-diffuse galaxy is exactly what the name implies. It's a galaxy that's physically large but extremely diffuse, meaning its stars are spread out over such a wide area that the galaxy has a very low surface brightness. If you measured the total amount of light it emits and then divided that by its size, you'd get a brightness per unit area that is many times fainter than a typical spiral or elliptical galaxy. To the human eye, and even to many telescopes, this faintness makes it nearly invisible. Here's the paradox of a UDG. They can be as large as the Milky Way in diameter, yet have only a fraction of its stars, sometimes just 1% or even less. The stars they do have are spread so thinly that the galaxy looks more like a dim haze than a structured object. Unlike dwarf galaxies, which are small and dim, UDGs are big and dim, vast cosmic footprints with barely any visible substance in them. Dragonfly 44 fits this category perfectly, and in fact, it's one of the poster children for what makes UDGs so fascinating. Measuring roughly 100,000 light-years across, it matches the Milky Way in physical size, but it contains only a few billion stars at most, far too few to create the glowing structure we're used to seeing in large galaxies. That's why it appears as such a faint, ghostly smear in images, rather than a bright spiral or a dense elliptical. The term ultra-diffuse galaxy didn't even exist in mainstream astronomy until relatively recently. For decades, these galaxies were overlooked simply because they are hard to detect. Their low surface brightness makes them blend into the background sky, so unless you're specifically looking for faint, extended objects, you might never know they're there. It wasn't until specialized instruments like the Dragonfly telephoto array came along that we began finding them in significant numbers. What makes Dragonfly 44 so special among UDGs is not just its faintness, but its mass. Most UDGs are thought to be puffed-up dwarf galaxies, low-mass systems that, for one reason or another, have been stretched out and spread thin. But Dragonfly 44 doesn't behave like a dwarf. Measurements of the speeds of its stars show that it has a gravitational pull comparable to the Milky Way, meaning it's surrounded by a massive dark matter halo. In other words, Dragonfly 44 is a giant galaxy disguised as a faint one, a heavyweight dressed up in the clothes of a lightweight. Being classified as a UDG also makes Dragonfly 44 part of a broader puzzle. Astronomers are still trying to figure out how galaxies in this category form in the first place. Did they start as normal galaxies that lost most of their gas and stopped making stars? Were they born in hostile environments like galaxy clusters, where interactions with other galaxies stripped them bare? Or do they represent an entirely different evolutionary path that we don't yet understand? In a way, calling Dragonfly 44 an ultra-diffuse galaxy is both a precise scientific description and a reminder of how strange it really is. The label captures its faintness and spread-out nature, but it doesn't fully convey the shock of its dark matter dominance. That's why Dragonfly 44 has become such an important case study. It forces scientists to ask whether UDGs as a whole might be more diverse, more massive, and more mysterious than we ever suspected. If UDGs are the ghosts of the galactic world, then Dragonfly 44 is one of the largest and most haunting specters we've ever encountered. And like any good ghost story, the real intrigue comes from how it was discovered in the first place, which, fittingly, is where we turn next. The story of Dragonfly 44's discovery begins in 2015, when a team of astronomers led by Peter van Dokkum of Yale University set out on a mission to map some of the faintest, most elusive galaxies in the universe. At the time, ultra-diffuse galaxies, UDGs, were just beginning to creep into the astronomical conversation, and many researchers suspected there might be far more of them lurking in deep space than anyone had realized. But to find them, you needed the right tools, and Van Dokkum's team had exactly that. They were using a new kind of telescope system called the Dragonfly telephoto array, which didn't look much like the giant domed observatories most people imagine when they think of astronomy. Instead, it was a strange and elegant arrangement of commercial telephoto camera lenses, each equipped with special nanostructure coatings to suppress internal reflections. This allowed the array to pick up extremely faint, extended light from galaxies that traditional telescopes would miss. The team aimed the Dragonfly array toward the Coma Cluster, a rich hunting ground for unusual galaxies. The Coma Cluster had already played a pivotal role in dark matter history. It's where Fritz Zwicky first proposed the idea in the 1930s, and its dense population of galaxies made it a prime place to search for faint outliers. In the images that came back, one object in particular caught their attention: a large, dim patch of light that had gone almost unnoticed in previous surveys. It was so faint that at first glance, you might mistake it for a background smudge or an imaging artifact. But its size and shape were unmistakable. It was a galaxy, and a big one at that. Follow-up observations quickly revealed just how unusual it was. Dragonfly 44 was huge, roughly the same size as the Milky Way, yet it was astonishingly dim, a textbook example of an ultra-diffuse galaxy. But its sheer scale set it apart from most other UDGs, which tend to be much smaller in mass. Van Dokkum and his colleagues knew immediately that this one warranted a closer look. The real turning point came when they began to measure the velocities of the stars in Dragonfly 44. To do this, they used the Keck Observatory in Hawaii, one of the most powerful optical telescopes in the world. By carefully studying the Doppler shifts in the light from the galaxy's stars, they could determine how fast those stars were moving around the galaxy's center. The results were jaw-dropping. The stars were moving so quickly that the galaxy's visible matter couldn't possibly be holding it together. Something massive and unseen was providing the gravitational glue, and that something was dark matter. When the team crunched the numbers, they realized that about 99% of Dragonfly 44's mass had to be dark matter. This was an unprecedented figure for a galaxy of its size, and it immediately made Dragonfly 44 one of the most extreme dark matter-dominated systems ever found. In August 2016, Van Dokkum and his team published their findings in the Astrophysical Journal Letters, and the astronomical community took notice. The idea that a Milky Way-sized galaxy could have almost no stars but still be held together by a massive dark matter halo challenged many existing ideas about galaxy formation. It was a discovery that didn't just add a new point to the cosmic map, it raised deep, unsettling questions about how galaxies come to be in the first place. What makes this discovery story even more compelling is the irony at its heart. A galaxy that is almost entirely invisible was found using an instrument named after one of nature's most delicate and visually striking creatures, the dragonfly. Without the Dragonfly telephoto array's unique ability to spot faint, extended light, Dragonfly 44 might still be hiding in the background noise of the Coma Cluster, its dark matter secrets untouched. The Dragonfly telephoto array is one of those inventions that makes you realize ingenuity in astronomy doesn't always mean build something bigger. Sometimes, it means build something different, and in this case, something that looks more like an art installation than a traditional observatory. If you picture a standard research telescope, you're probably imagining a massive tube inside a dome, with a giant mirror collecting light from distant stars. The Dragonfly array breaks that mold entirely. Instead of a single giant lens or mirror, it's made up of multiple commercial telephoto camera lenses, the kind used by professional wildlife or sports photographers. Each lens is mounted on a motorized tracking system, and all of them are carefully aligned to point at the same patch of sky. When Dragonfly 44 was discovered, the array consisted of just 8 Canon 400mm f2.8 lenses, but it has since grown to dozens of them. The setup looks a bit like a bouquet of oversized camera lenses mounted on a metal framework, all working together to collect light. The array part of the name comes from the fact that each lens acts like its own telescope, and the images from all lenses are combined to produce an ultra-sensitive final image. So why go with telephoto camera lenses instead of traditional telescope optics? The answer lies in the problem of low surface brightness. Many telescopes, especially large ones, are great for high-contrast, sharp images of bright objects, but they suffer from internal reflections and scattering that can overwhelm faint, diffuse light. This makes it hard to detect the ghostly glow of something like Dragonfly 44. The Dragonfly telephoto arrays lenses are equipped with nanofabricated coatings that minimize reflections to an extraordinary degree. These coatings were originally developed for cutting-edge photography and sports broadcasting, but they turn out to be perfect for astronomy's most subtle targets. With almost no internal glare, the array can pick up incredibly faint, widespread light sources, exactly the kind of signal that ultra-diffuse galaxies give off. The name Dragonfly wasn't just chosen because it sounds nice. Dragonflies in nature have exceptionally sharp, multilensed vision. Their compound eyes allow them to detect subtle movements and details that other creatures miss. The telescope array's designers thought that was a fitting metaphor for their instrument, a set of multiple eyes scanning the sky for the faintest glimmers of light. Just as a dragonfly can spot a tiny insect mid-flight, the Dragonfly telephoto array can pick out the most delicate traces of a galaxy hiding in the cosmic background. There's also a poetic twist. The Dragonfly is an agile, light, and elegant flyer, and the array itself is relatively lightweight compared to a traditional telescope of similar light-gathering power. Instead of building one enormous optical system, the team can simply add more lenses to the array as funding and resources allow. This modular design means its sensitivity can grow over time. More eyes means more light collected, and more faint galaxies revealed. In a sense, the Dragonfly array represents a revolution in thinking. It proves that you don't need to spend billions of dollars to make groundbreaking discoveries. Sometimes, combining clever design with existing technology can open entirely new windows into the universe. Dragonfly 44 is the perfect example of this. A galaxy that might have remained invisible to massive, expensive observatories was instead spotted by what's essentially a team of high-end telephoto lenses working in harmony. The reason Dragonfly 44 and other galaxies like it stayed hidden for so long comes down to one deceptively simple concept: surface brightness. When astronomers talk about how bright something appears, they're not just thinking about the total amount of light it emits, but also about how that light is spread out. You can have two objects that emit the same total light, but if one is compact and concentrated, it will appear bright, while the other, if spread over a huge area, will look faint and washed out. Dragonfly 44 is the latter. It's big as the Milky Way in diameter, but its few billion stars are scattered across that enormous space like a handful of grains spread over a football field. The result is that each square arc-second of the galaxy on the sky emits almost no detectable glow. Even though the galaxy as a whole contains a lot of stars, the light per unit area is so low that it blends into the background. Here's the problem for traditional telescopes. They're optimized for point sources or relatively bright, concentrated structures, stars, compact galaxies, planetary nebulae, etc. They're not designed to easily detect faint, diffuse fuzz. In fact, many observatories are hindered by internal reflections, scattered light, and detector noise, all of which can mimic or mask the soft glow of an ultra-diffuse galaxy. To make matters worse, Earth's atmosphere adds its own challenge. The sky isn't truly dark. Even on the clearest nights, there's a natural background brightness from airglow, scattered moonlight, and light pollution. If a galaxy's surface brightness is close to or below that background level, it's almost impossible to spot unless you have an instrument tuned specifically for such subtle signals. It's not that astronomers didn't look at the region where Dragonfly 44 is. The Coma Cluster has been imaged countless times. The issue is that, in most images, Dragonfly 44 would just appear as a pale smudge, indistinguishable from noise unless you were specifically hunting for ultra-diffuse structures. Many surveys simply overlooked it because it didn't fit the bright, sharp profile of the galaxies they were cataloging. Think of it like trying to spot a faint pencil drawing on a slightly smudged piece of paper. If your eyes are trained to look for bold ink lines, you might glance right over it. Only when you tune your vision for faint pencil marks will the image emerge. The Dragonfly telephoto array essentially gave astronomers that tuned vision. There's also an observational bias at play. For decades, galaxy surveys focused on luminous galaxies because they're easier to study. More light means you can gather more detailed data in less time. Ultra-diffuse galaxies, by contrast, require long exposure times to build up enough signal to separate them from the background. In large surveys covering millions of objects, time is precious, and faint smudges often get pushed aside in favor of brighter targets. So Dragonfly 44's invisibility was really a combination of factors. Its low surface brightness made it difficult to distinguish from background noise. Traditional telescope's optical designs scattered too much light internally to reliably detect such diffuse targets. Atmospheric and environmental effects further masked its presence. Survey strategies tended to ignore faint extended objects in favor of luminous galaxies. In hindsight, it seems remarkable that such a massive, Milky Way-sized galaxy could go unnoticed in such a well-studied region of the sky. But that's the humbling thing about astronomy. The universe hides its biggest secrets in plain sight, relying on our assumptions to keep them invisible. Dragonfly 44 wasn't hiding behind anything. It was hiding within the data all along. Measuring the mass of a galaxy like Dragonfly 44 is not as simple as putting it on a cosmic scale. We can't weigh it directly. Instead, astronomers have to work like detectives, using indirect evidence to figure out the total mass. In this case, the key clue came from the speeds at which the galaxy's stars move. The method is rooted in Newtonian physics and the virial theorem, which essentially says that the motions of objects in a gravitational system are directly related to the amount of mass that system contains. If you see stars orbiting quickly within a galaxy, you can infer that there's a lot of gravitational pull, and therefore a lot of mass, holding them in place. Here's how the process worked for Dragonfly 44. 1. Choose tracer stars. Because Dragonfly 44 is so faint, astronomers couldn't just observe a dense field of bright stars as they might with a luminous galaxy. They had to identify specific stars and globular clusters orbiting the galaxy that were bright enough to be seen from Earth and representative of the galaxy's motion as a whole. 2. Collect spectra. Using the Keck 2 telescope in Hawaii, one of the most powerful optical telescopes in the world, they captured spectra of these stars. A spectrum is like a barcode of light. It shows how much light is emitted at each wavelength. When a star is moving toward us, its spectral lines shift slightly toward the blue end of the spectrum. When it moves away, they shift toward the red end. This is the Doppler effect in action. 3. Measure Doppler shifts. By precisely measuring how much the spectral lines shifted, the team could calculate the star's velocities relative to us. This isn't about one star's motion, but rather the statistical spread of velocities, known as the velocity dispersion, across many stars in the galaxy. 4. Link velocities to mass. Once they had the velocity dispersion, they could plug that into gravitational models to estimate the galaxy's total mass. The faster the stars move, the more massive the galaxy must be to keep them gravitationally bound. When Van Dokkum's team ran the numbers, they found something astonishing. The stars in Dragonfly 44 were moving far faster than they would if the galaxy's visible stars were the only source of mass. In fact, based on the galaxy's faint light, its stellar mass was only about 1% of what would be needed to explain those high speeds. The rest of the mass had to be coming from something invisible, dark matter. The final estimate put Dragonfly 44's total mass at roughly 1 trillion solar masses, comparable to the Milky Way's mass, but with only about 1% of that in normal matter like stars and gas. That meant 99% of its mass was dark matter, making it one of the most dark matter-dominated galaxies ever discovered. This measurement wasn't just impressive, it was surprising even to experts. Ultra-diffuse galaxies had been seen before, but none with such an extreme mass-to-light ratio on this scale. For comparison, the Milky Way's dark matter content is high, but only around 85 to 90% of its total mass. Dragonfly 44 pushed that number right up to the theoretical edge. And this wasn't a one-off fluke in the data. The velocity measurements were repeated and cross-checked, and while later studies refined the numbers slightly, the conclusion held: this galaxy is overwhelmingly made of dark matter. It's worth noting that in astronomy, measuring something so faint, so far away, and so diffuse is not easy. These results depended on some of the largest telescopes in the world, long exposure times, and careful statistical analysis. The fact that the team could pull such a clear signal from such a ghostly galaxy is a testament to how far observational techniques have come. When the first detailed mass measurements for Dragonfly 44 were announced in 2016, they didn't just cause raised eyebrows in the astronomy community, they caused outright disbelief in some corners. Astronomers had known for decades that dark matter makes up the bulk of the mass in most galaxies. Spiral galaxies like the Milky Way, for example, show flat rotation curves. Their stars at the edges move just as fast as those near the center, implying there's an invisible gravitational glue holding everything together. But even in these cases, normal matter, stars, gas, dust, still accounts for 10 to 15% of the total mass. Dragonfly 44 obliterated that expectation. The data showed that 99% of its mass is dark matter, leaving just 1% in normal matter, and even that was spread so thin across a galaxy the size of the Milky Way that it barely registered in optical images. For many astronomers, the first reaction was, "Are you sure about this?" The Coma Cluster had been studied in depth for decades, and yet here was a Milky Way-sized object hiding in plain sight, with the most extreme mass-to-light ratio seen in a galaxy of that scale. It wasn't just that it was unusual, it challenged models of how galaxies form. At the time, theoretical frameworks predicted that galaxies of this size should have undergone enough star formation to produce a visible, luminous population. Something must have gone very differently for Dragonfly 44. Did it form normally but somehow lose nearly all its stars and gas? Or did it fail to ignite star formation in the first place? Either scenario implied unusual, possibly violent evolutionary processes. The shock was amplified by the fact that ultra-diffuse galaxies, UDGs, were only just beginning to be catalogued in large numbers. Many of them were low in stars, but Dragonfly 44 seemed to be on a different level entirely, the poster child for a galaxy built almost entirely out of the invisible stuff. The discovery also reignited debates about the nature of dark matter itself. If an entire galaxy could be made of the stuff, it offered a new kind of laboratory for testing dark matter theories. Some physicists speculated that Dragonfly 44 might reveal how dark matter clumps together on galactic scales. Others saw it as a challenge to alternative gravity theories, which try to explain away dark matter by modifying the laws of gravity. In such a diffuse, low-luminosity galaxy, those models struggle to match the observed stellar motions. The media picked up on the discovery quickly, with headlines calling it the invisible galaxy, ghost galaxy, or dark matter galaxy. While these names were catchy, they also reflected genuine scientific astonishment. This wasn't a minor oddity tucked away in a corner of the sky. It was a major outlier sitting in one of the most heavily studied clusters in the universe. Van Dockum himself expressed surprise at the findings, noting that they had expected to see some contribution from normal matter, but the measurements kept pointing to the same staggering ratio. The data suggested that whatever normal matter the galaxy started with had been stripped away or suppressed, leaving a massive halo of dark matter holding together a sparse scattering of stars. It wasn't just the dark matter percentage that shocked people, it was the scale of it. Astronomers had seen dwarf galaxies with high dark matter fractions before, but this was a Milky Way-sized system with the same level of dominance. That combination was new, and it hinted that the universe might be hiding many more such objects from view. In short, Dragonfly 44 didn't just enter the astronomical literature, it exploded into it. In a field where most discoveries are refinements or incremental steps, this was a jump, from knowing ultra-diffuse galaxies existed to realizing one could be almost pure dark matter. The discovery of Dragonfly 44 instantly elevated it from a curious oddball to a potential gold mine for dark matter research. In astrophysics, finding a system that's 99% dark matter is like stumbling across a pure, undisturbed sample of a rare element in nature. It's not just interesting, it's priceless. The problem with studying dark matter in most galaxies is that normal matter, stars, gas, dust, black holes, gets in the way. All those luminous components not only add their own gravitational pull, but they also interact with each other, creating complex dynamics that can blur the signature of the dark matter halo. In other words, in a typical galaxy, dark matter is the dominant player, but it has to share the stage with a noisy cast of bright, messy co-stars. Dragonfly 44 is different. Here, normal matter is so scarce that its gravitational influence is almost negligible compared to the halo. This makes it a near-ideal clean room environment for measuring the distribution, density, and structure of dark matter on galactic scales. This is important for several reasons. 1. Testing dark matter halo models. The standard cosmological model predicts that galaxies are embedded in vast halos of dark matter, often extending far beyond the visible boundaries of the stars. By measuring how mass is distributed in Dragonfly 44, using stellar velocities, globular cluster motions, and perhaps even gravitational lensing in the future, scientists can test whether the halo's shape and density profile match predictions from simulations. If Dragonfly 44's halo turns out to be unusually massive or structured differently from the theoretical models, it could point to flaws in our understanding of how dark matter clumps and behaves over time. 2. Constraining dark matter particle properties. Different dark matter candidates, such as WIMPs, weakly interacting massive particles, actions, or sterile neutrinos, predict different small-scale behaviors for halos. For example, some theories suggest that dark matter should be cold and cluster tightly, while others propose that it should be more diffuse or warm. In galaxies like Dragonfly 44, where almost all the gravity is dark matter's doing, subtle features in the halo could hint at which of these models is correct. 3. Understanding galaxy formation extremes. Dragonfly 44 sits at the edge of what we thought was possible in galaxy evolution. If it formed with such a massive dark matter halo, why did it fail to form a proportional amount of stars? Was its gas stripped away by the dense Coma Cluster environment before it could ignite? Was star formation suppressed by feedback from supernovae or an early active black hole? Whatever happened, the process seems to have left the dark matter halo largely untouched, offering a snapshot of a failed galaxy, a massive halo without the luminous component we'd normally expect. Studying it might reveal not just dark matter properties, but also why galaxies sometimes don't grow as planned. 4. Providing a counterpoint to dark matter-free galaxies. Interestingly, in 2018 Van Dockum and his team announced galaxies, like NGC 1052 DF2, that seem to contain almost no dark matter at all. Those claims are still debated, but if true, they form an intriguing mirror to Dragonfly 44. One galaxy almost entirely dark matter, another almost entirely without it. Comparing the two extremes could help explain the role dark matter plays in shaping galaxy properties. 5. Improving gravitational lensing studies. If astronomers can confirm the mass and shape of Dragonfly 44's halo precisely, it could serve as a calibration tool for gravitational lensing models. Even though the galaxy itself is faint, its mass might bend the light of background galaxies, offering another way to study its dark matter distribution. In short, Dragonfly 44 isn't just a curiosity, it's a natural laboratory, the kind of rare cosmic specimen that could help pin down one of the deepest mysteries in science. For decades, dark matter has been an inference, something we detect only through its gravitational pull. A galaxy that's almost pure dark matter lets us strip away most of the noisy complications and stare directly at the phenomenon itself. For scientists trying to answer the question, what is dark matter? This is as close as we've come to having a dedicated test case, a place where nature has done the isolating experiment for us. When you put Dragonfly 44 side by side with the Milky Way, it's almost like comparing two people of the same height and build, but one is a bodybuilder, and the other is a ghost. On paper, they're similar in size and total gravitational heft, yet visually and structurally, they couldn't be more different. Size and mass. Both the Milky Way and Dragonfly 44 measure roughly 60,000 to 100,000 light-years across. In terms of total mass, they're also surprisingly similar. Each tips the cosmic scale at close to 1 trillion solar masses. But here's the catch. In the Milky Way, that trillion solar masses includes a substantial chunk of stars, gas, dust, planets, and other luminous matter. In Dragonfly 44, almost all of that mass is dark matter. This difference is like having two identical containers of the same weight, except one is filled with gold coins you can see and count, and the other is packed with invisible bricks that you can only detect by how heavy it feels. Star count. The Milky Way is home to somewhere between 200 billion and 400 billion stars. It's rich in dense star clusters, sprawling spiral arms, glowing nebulae, and all the visual hallmarks of an active, vibrant galaxy. Dragonfly 44? It has maybe a few 100 million stars, about 1% of the Milky Way stellar population, scattered so sparsely that even its central regions look thin and ghostly. To put it in perspective, if the Milky Way stars were people in a bustling city, Dragonfly 44 would be like a rural county with the same borders as New York City but only a couple of small towns inside. Brightness and appearance. The Milky Way shines with an absolute magnitude around -21, making it a brilliant spiral visible from great distances. Dragonfly 44's brightness is so low that it's barely detectable even with long-exposure imaging through specialized telescopes. Astronomers classify it as having low surface brightness, so faint that to the naked eye, if you could somehow travel there and look from nearby, it might appear as a dim, fog-like haze with scattered pinpricks of light. Structure. The Milky Way's spiral arms and central bulge are sculpted by density waves, star formation, and the gravitational influence of its bar-shaped core. Dragonfly 44 lacks such dramatic features. It has no prominent spiral structure, no dense bar, and no central superbright bulge. Its stars are spread over a diffuse disk or spheroidal region, without the organized patterns that gas-rich, star-forming galaxies display. Gas and star formation. The Milky Way is rich in interstellar gas and dust, fueling ongoing star formation. Giant molecular clouds, like the Orion Nebula, are stellar nurseries creating new stars all the time. Dragonfly 44, on the other hand, appears almost barren of gas. Without that fuel, star formation is minimal or non-existent. Its few stars are largely old, meaning whatever star-forming activity it once had likely shut down billions of years ago. Dark matter ratio. In the Milky Way, about 85 to 90% of the mass is dark matter, leaving 10 to 15% in normal matter. That's already a strong dominance of dark matter, but Dragonfly 44 takes it to the extreme, with 99% dark matter and just 1% normal matter. Implications of the contrast. When astronomers see a massive galaxy like the Milky Way, the dark matter halo explains the extra gravitational pull that luminous matter alone can't account for. In Dragonfly 44, the luminous matter is so scarce that it's almost irrelevant to the galaxy's total gravitational profile. This contrast tells us something profound. Dark matter isn't just a supporting player in galaxy formation. In some cases, it's the entire story. If the Milky Way represents the standard outcome of cosmic evolution, a harmonious mix of dark matter and visible matter, then Dragonfly 44 is the extreme counterexample. It challenges the idea that a galaxy's mass is a good predictor of how many stars it will have. Apparently, you can have the mass of a Milky Way and the starlight of a modest dwarf galaxy. If the universe were a city, the Coma Cluster would be one of its busiest downtown districts, a dense, bustling hub packed with thousands of galaxies, immense clouds of hot gas, and the invisible scaffolding of dark matter stretching over millions of light-years. Dragonfly 44 lives right in the middle of this cosmic metropolis. It's not hanging out on the quiet fringes of space. It's deep inside a gravitational superneighborhood, surrounded by some of the largest and most massive galaxies in the observable universe. The scale of the Coma Cluster. The Coma Cluster sits about 330 million light-years away from us in the constellation Coma Berenices. It contains more than 1,000 identified galaxies, and possibly thousands more faint ones, all bound together by a gigantic dark matter halo whose mass is estimated at over a quadrillion, 10 to the power of 1, times that of the Sun. It's so massive that its gravity warps space-time, creating gravitational lensing effects that bend light from even more distant galaxies behind it. This cluster is part of an even larger cosmic structure, the Coma supercluster, linking it to other galaxy clusters through vast filaments of dark matter and intergalactic gas. The giants of Coma. Dominating the Coma cluster are two colossal elliptical galaxies, NGC 4874 and NGC 4889. These monsters are among the largest galaxies known, each spanning hundreds of thousands of light-years and containing trillions of stars. Around them swarm smaller ellipticals, lenticulus, and spirals, along with a population of ultra-diffuse galaxies like Dragonfly 44. Compared to the luminous giants, Dragonfly 44 is a ghostly shadow, but gravitationally, it still holds its own because of its massive dark matter halo. In the Coma cluster's crowded environment, size and brightness aren't always the same thing. The intracluster medium, ICM. One of the defining features of the Coma cluster is its intracluster medium, an enormous reservoir of extremely hot, X-ray emitting gas that fills the space between galaxies. This gas is heated to tens of millions of degrees by the cluster's gravitational collapse, and it's so dense, by intergalactic standards, that it can strip gas from galaxies passing through it at high speed. This process, known as ram pressure stripping, could be a key player in Dragonfly 44's history. If Dragonfly 44 ever had a healthy supply of cold gas for star formation, passing through the ICM could have swept that gas away like wind blowing through an open window, shutting down its ability to make new stars. High-speed encounters. In a cluster as packed as Coma, galaxies don't just float peacefully, they move fast. Speeds can reach over 1,000 kilometers per second as galaxies orbit the cluster's center of mass. These high-speed flybys can gravitationally disturb galaxies, stretching and distorting them, or even pulling stars and gas out entirely. Dragonfly 44 may have been shaped by these tidal interactions. Repeated encounters with massive neighbors could have puffed it up into its current ultra-diffuse form, while also depleting it of much of its visible matter. Why the environment matters. The Coma Cluster's crowded, turbulent conditions offer a possible explanation for how a galaxy like Dragonfly 44 ended up with so few stars yet so much mass. In such an environment, a gas can be stripped before it ever forms stars. A stellar material can be tidally removed by giant neighbors. A star formation can be suppressed by repeated shocks from cluster activity. All of this fits with the idea that Dragonfly 44 might be a failed giant, a galaxy that started out with the potential to become bright and spiral-armed, but had its growth halted by the hostile cluster environment. A difficult place to hide. Yet it did. What's most remarkable is that Dragonfly 44 managed to remain undiscovered for so long in one of the most intensely studied galaxy clusters in the sky. The Coma Cluster has been photographed and catalogued for decades, but its low surface brightness meant that Dragonfly 44 blended into the background, invisible to traditional surveys. It took the specialized eyes of the Dragonfly telephoto array to finally bring it into view. In a sense, Dragonfly 44's home is part of the paradox. It lives in a blindingly bright city of galaxies, yet it's one of the dimmest, most elusive residents. If you could somehow aim the Hubble Space Telescope or one of the world's giant ground-based observatories at Dragonfly 44, you might expect to see a dazzling galactic disk brimming with stars. Instead, you'd probably squint at the screen, wondering if the image file had failed to load. That's because Dragonfly 44 suffers from one of the most extreme cases of low surface brightness, LSB, astronomers have ever documented. Its stars are spread out so thinly across such a large area that, even though the galaxy's total size rivals the Milky Way, the average amount of light per unit area is minuscule. What low surface brightness means. Surface brightness isn't about how bright an object appears overall, it's about how much light it emits per square arcsecond of sky. A compact object like a star or small galaxy can appear bright because all its light is concentrated in a tiny spot. But when the same amount of light is smeared across a vast area, the brightness per pixel drops dramatically. Dragonfly 44 is the galactic equivalent of smearing a teaspoon of sugar over a football field. The sweetness is still there, but it's so thinly distributed you'd barely taste it. Why this makes it hard to detect. Astronomical imaging isn't just about collecting light, it's about distinguishing that light from the background noise of the sky. The faint glow from the Earth's atmosphere, for ground-based telescopes, scattered starlight, and even cosmic background radiation can overwhelm extremely diffuse light sources. When astronomers tried to spot Dragonfly 44 using conventional telescopes with reflective mirrors, it simply vanished into the noise. Its faint smudge was indistinguishable from the random fluctuations in the background. The ghostly appearance. When the Dragonfly telephoto array finally imaged Dragonfly 44, it appeared as a barely perceptible oval haze, with only a handful of brighter stars visible, and most of those weren't even part of the galaxy, but foreground stars from our own Milky Way. This lack of prominent structure is part of what makes ultra-diffuse galaxies like Dragonfly 44 so eerie. They don't have the bold spiral arms of the Milky Way, the compact ellipsoidal glow of a dwarf elliptical, or the bright knots of star-forming regions. Instead, they look like the lingering smoke of a candle, faint, formless, and transient-looking, even though they've been around for billions of years. Why even big telescopes struggle. You might think a massive observatory like the Keck telescope or the Very Large Telescope could easily pick up something like Dragonfly 44. But the problem isn't raw light-gathering power, it's contrast. Low-surface brightness galaxies are difficult because the sky background is brighter than the galaxy's average pixel brightness. Our optical scattering in large mirrors can blur faint features, effectively washing them out. Data processing often filters out what appears to be faint haze as noise unless astronomers know to look for it. This is why the Dragonfly telephoto array, with its ultra-low scatter refractive lenses, could see it when others couldn't. Compounding the problem: distance. If Dragonfly 44 were in our local group, say, sitting next to the Andromeda Galaxy, we'd have an easier time detecting and studying it. But it's 330 million light-years away in the Coma Cluster. That enormous distance means every star is not only faint but also compressed into a tiny angular footprint on the sky. To see it clearly, astronomers need long exposure times and specialized optics tuned to detect extended, diffuse light. Observing consequences. Because of its faintness. Measuring its stellar velocities requires targeting the few bright globular clusters it hosts, rather than the galaxy's general starlight. Mapping its dark matter halo demands careful modeling to account for the scarcity of tracers. Tracking any internal structural details is almost impossible. We see it more as an outline of starlight than as a richly detailed object. The irony. Despite being nearly the same size as the Milky Way, Dragonfly 44 is so dim that it could fit behind some of the brighter galaxies in the Coma Cluster without anyone noticing. Its ghost-like appearance is exactly why it eluded detection for so long, and why astronomers believe there could be countless other ultra-diffuse galaxies hiding in plain sight across the universe. While Dragonfly 44 may be one of the most famous examples of an ultra-diffuse galaxy, UDG, it's not the only one haunting the cosmos with a ghostly presence. In fact, astronomers now suspect that UDGs might be surprisingly common, especially in galaxy clusters like Coma. But even among this spectral population, Dragonfly 44 stands out as one of the most extreme and intriguing. The rise of the ultra-diffuse galaxy class. The term ultra-diffuse galaxy describes a galaxy that is physically large, often Milky Way-sized in diameter, but incredibly dim because its stars are spread so thinly. Their low surface brightness makes them difficult to detect, and until the last decade, they were mostly invisible to traditional surveys. When the Dragonfly telephoto array first began systematically searching for such objects, astronomers discovered dozens of these wispy giants in the Coma Cluster alone. This was a revelation. The Coma Cluster had been studied for decades, yet these ghost galaxies had remained hidden in plain sight. The known population. Some well-known examples besides Dragonfly 44 include a Dragonfly 17, another Coma Cluster UDG, similar in size but less massive. DFX1, a UDG with signs of tidal disruption, indicating gravitational harassment from nearby galaxies. VCC 1287, found in the Virgo cluster, this galaxy also has an unusually high dark matter content. DF2 and DF4, located in the NGC 1052 group, these two UDGs made headlines because initial measurements suggested they might lack dark matter almost entirely, the polar opposite of Dragonfly 44. Later studies refined those numbers, but the controversy highlighted just how varied UDGs can be. Why Dragonfly 44 is still exceptional. Even within this family of ultra-diffuse galaxies, Dragonfly 44 is a heavyweight champion in one specific category: dark matter dominance. Most UDGs have high dark matter fractions, often above 80 to 90%, but Dragonfly 44's 99% dark matter content puts it at the extreme end. It's not just dim, it's almost entirely invisible matter. In addition, its total mass is enormous for a UDG, rivaling that of the Milky Way. This combination of mass, size, and faintness makes it a rare and valuable case for studying the relationship between dark matter and galaxy formation. Possible formation scenarios for UDGs. Astronomers have proposed several ideas for how UDGs form. 1. Failed giants. Galaxies that started with massive dark matter halos but lost or never acquired enough gas to form many stars. 2. Puffed-up dwarfs. Small galaxies that were stretched by tidal interactions or gas outflows, making them larger but not more luminous. 3. Environmental victims. Galaxies whose gas was stripped away early by the harsh environment of a cluster, halting star formation prematurely. Dragonfly 44 could fit into any of these scenarios, but its extreme mass makes the failed giant hypothesis especially compelling. Why UDGs matter to astronomy. Ultra-diffuse galaxies, as a class, are important for several reasons. They test galaxy formation models. We need to explain how galaxies of similar size can have such radically different star counts. They offer natural laboratories for studying dark matter, Their high dark matter fractions make gravitational effects easier to measure without interference from dense stellar populations. They may hold clues about galaxy cluster evolution, particularly how dense environments strip and transform galaxies over time. Dragonfly 44, the poster child. While other UDGs may rival it in size or in darkness, none has captured the public imagination quite like Dragonfly 44. It's the galaxy that shattered expectations, a system as massive as our own but nearly starless, invisible except for its ghostly shimmer. It has become the archetype for explaining what UDGs are, and a key target for astronomers trying to pin down the nature of dark matter itself. When Dragonfly 44 first made headlines in 2016 as a galaxy with the mass of the Milky Way but only 1% of its stars, the claim was so extraordinary that it immediately invited skepticism. In astronomy, when you see something that doesn't fit the established picture, there are usually two possibilities. You've discovered a genuine outlier, or you've run into a measurement problem. With Dragonfly 44, both possibilities were on the table. The heart of the debate. The big, shocking number, that 99% of its mass is dark matter, comes from measuring the velocities of stars and globular clusters orbiting within the galaxy. Higher velocities mean more gravitational pull, which means more mass. But in Dragonfly 44's case, astronomers couldn't measure the velocities of individual stars directly because it's so faint. Instead, they used a small sample of bright globular clusters around the galaxy as traces of its gravitational potential. This is where the debate begins. Was the sample size too small to be statistically solid? Were the clusters moving in ways that fairly represented the galaxy's total mass distribution? Could projection effects, how we see the motion from Earth's point of view, have biased the numbers? Sample size concerns. The initial velocity dispersion, a measure of how fast the tracers were moving, was based on fewer than 24 globular clusters. Some astronomers argued that with such a small data set, a few outlier measurements could dramatically skew the inferred mass. Others pointed out that globular clusters may not perfectly trace the galaxy's gravitational potential. They could be on elongated orbits, or even temporarily passing through from tidal encounters, which would make them appear faster than they should be. Alternate interpretations. Several alternate explanations for Dragonfly 44's extreme mass-to-light ratio were floated. 1. Overestimated mass. If the velocity dispersion was accidentally inflated due to a statistical fluke or projection bias, the galaxy might be less massive than claimed. 2. Overcounted globular clusters. If some of the objects were misidentified as globular clusters when they were actually background galaxies, the dynamics could be misread. 3. Unusual kinematics. The globular clusters might not be in equilibrium with the galaxy's gravity, especially if Dragonfly 44 has been tidally disturbed recently. The role of environment in confusion. Being in the dense Coma Cluster complicates things. Interactions with nearby galaxies or the cluster's gravitational field could fling globular clusters into unusual orbits, making them poor proxies for the galaxy's total gravitational mass. Follow-up studies. Later observations using more data refined Dragonfly 44's velocity dispersion and slightly lowered the mass estimate, but it still remained exceptionally dark matter-dominated. The revised numbers didn't erase its status as a dark matter-rich UDG, they simply brought the figure down from jaw-dropping to still incredibly strange. The consensus now is that while the first mass estimate may have been on the high side, the core finding, that Dragonfly 44 is overwhelmingly made of dark matter, holds up. Why the debate matters. Science thrives on challenge. Extraordinary claims demand extraordinary evidence, and the initial pushback forced astronomers to dig deeper, gather better data, and test the robustness of their conclusions. Far from undermining the discovery, the debates have made the case for Dragonfly 44 stronger, because the follow-up studies were designed specifically to rule out the most obvious sources of error. After the initial 2016 announcement that Dragonfly 44 was essentially a ghostly twin of the Milky Way made almost entirely of dark matter, the astronomy community wanted verification. The claim was simply too big to rest on a single set of measurements, especially ones based on a small number of globular cluster velocities. That led to a series of follow-up observations over the next few years, each designed to test and refine the original findings. Expanding the dataset. One of the first priorities was to increase the sample size for velocity measurements. The original study had fewer than 24 globular clusters to work with. Later teams used larger telescopes and longer exposure times to detect fainter globular clusters around Dragonfly 44, expanding the pool of tracers. With more data points, they could more accurately determine the velocity dispersion, the spread in speeds of objects orbiting within the galaxy. This helps smooth out the statistical noise that comes from relying on only a handful of measurements. Refining the velocity dispersion. The initial 2016 paper estimated a velocity dispersion of about 47 km per second, which translated into a Milky Way-sized dark matter halo. Subsequent measurements, using more precise instruments like the Keck Observatory's Deimos spectrograph, found a somewhat lower velocity dispersion, closer to 30 km per second. This adjustment reduced the estimated total mass of Dragonfly 44. Instead of being exactly Milky Way massive, it now appeared to have a halo roughly half to two-thirds that size. But, and here's the important part, its stellar mass stayed the same, which meant its mass-to-light ratio was still enormous, and its dark matter fraction still hovered around 95 to 99%. Deep imaging campaigns. Teams also used deep imaging from both ground-based and space telescopes to get better pictures of Dragonfly 44's structure. This helped in two ways. 1. Globular cluster census. By cataloging exactly how many globular clusters it hosts, astronomers could compare it to galaxies of known mass, since there's a rough correlation between halo mass and cluster count. Dragonfly 44's globular cluster population was still consistent with a very massive halo, supporting the dark matter-rich interpretation. 2. Environmental checks. Deep imaging could reveal signs of tidal disruption, stretched streams of stars, distorted shapes, which might suggest the galaxy was being gravitationally disturbed, making mass estimates unreliable. While Dragonfly 44 does show some irregularities, nothing indicated catastrophic tidal stripping that would invalidate the measurements. Confirming the dark matter story. By 2019 and 2020, after multiple independent studies, the consensus was that the exact mass of Dragonfly 44 may be a bit lower than first reported. It is still an extremely dark matter-dominated ultra-diffuse galaxy. Its properties remain highly unusual, especially given its large size and sparse stellar population. In other words, the core mystery stood firm. Here is a massive galaxy halo that somehow failed to turn its cosmic raw material into stars, leaving it as a ghostly relic dominated almost entirely by dark matter. The broader impact of follow-up studies. These follow-up observations not only confirmed Dragonfly 44's status but also demonstrated the importance of multi-step verification in astronomy. The process strengthened the reliability of the data and pushed forward techniques for measuring mass in extremely faint galaxies. It also inspired new surveys looking specifically for dark matter-rich ultra-diffuse galaxies in other clusters, opening up a whole new branch of observational cosmology. If there's one thing that Dragonfly 44 makes crystal clear, it's that galaxy formation is not a simple, one-size-fits-all process. For decades, astronomers worked with a broad, but fairly predictable, pattern. A galaxy's dark matter halo mass sets the stage for how much gas it can gather, which in turn sets the pace of star formation. The more massive the halo, the deeper its gravitational well, meaning it should be able to hang on to gas and churn out billions upon billions of stars. Dragonfly 44 laughs in the face of that neat little rulebook. The standard picture, and YD44 breaks it. In the lambda cold dark matter, CDM, cosmological model, galaxies form when matter clumps together in dark matter halos, pulling in gas that cools and condenses into stars. A halo as large as Dragonfly 44's should, in theory, host a luminous, bustling spiral galaxy with hundreds of billions of stars, something like the Milky Way. Instead, Dragonfly 44 is the opposite, an enormous dark matter halo with almost no stellar payoff. This is like finding a fully built sports stadium, with only a handful of fans in the seats. Possible clues from Dragonfly 44's formation. Astronomers have brainstormed several ways such a galaxy could form. 1. Gas loss before star formation began. Dragonfly 44's halo may have formed normally, but perhaps it lost its gas early, possibly stripped away by the hot plasma in the Coma Cluster before the gas could cool into stars. This would freeze the galaxy in an embryonic state, leaving the massive dark matter structure but almost no visible matter. 2. Catastrophic star formation shutdown. The galaxy might have started forming stars normally, but an early event, like a burst of intense supernova activity or a close encounter with another galaxy, could have blown out its remaining gas, halting star formation prematurely. 3. Star formation never got going. Some models suggest that under certain conditions, perhaps due to the heating effects of the early cosmic ultraviolet background, gas simply never cools efficiently inside a massive halo, preventing large-scale star formation altogether. 4. Tidal ghost creation. There's also the possibility that Dragonfly 44 is the remnant of a once normal galaxy that was violently stripped of its stars by repeated gravitational encounters, leaving behind the dark halo and a sprinkling of stars. But this is less favored, as the galaxy's structure doesn't fully match a heavily stripped system. Why this matters for galaxy formation theory. Dragonfly 44 forces astronomers to confront the reality that halo mass alone is not destiny. Star formation efficiency, the percentage of available matter converted into stars, can vary dramatically, even among halos of similar mass. This raises deep questions. Are ultra-diffuse galaxies like Dragonfly 44 rare cosmic accidents, or are they a common but overlooked outcome of galaxy formation? Or do they form in special environments, like dense clusters, that make them more likely? Or could some of them exist in isolation, invisible to us simply because they're so faint? D44 as a cosmic laboratory. Dragonfly 44 also provides a unique opportunity. Because its stars are so sparse, their gravitational influence is minimal compared to the dark matter halo. That means astronomers can study the halo's properties in a clean way, without the complication of dense stellar matter muddying the mass measurements. It's like studying a building's steel skeleton without all the walls and furniture in the way, a rare chance to examine the underlying structure of a galaxy in isolation. The broader implication. If galaxies like Dragonfly 44 are more common than we thought, it suggests that the universe is home to many failed giants, halos that should be teeming with stars but aren't. That changes how we model galaxy population statistics and could influence our understanding of both cosmic evolution and dark matter physics. When astronomers talk about a dark matter halo, they're not picturing something glowing or ring-like around a galaxy. Instead, a dark matter halo is an invisible, three-dimensional cloud, vast, diffuse, and completely transparent, that surrounds and permeates a galaxy. It's not just a shell, it's the galaxy's true skeleton, the gravitational backbone that holds everything together. The invisible scaffold of the universe. According to modern cosmology, galaxies don't simply float in space, assembling themselves from random clumps of stars. Instead, they are born inside these enormous halos of dark matter. The halo's gravity pulls in regular matter, gas and dust, and over cosmic time, that matter cools and condenses into stars. The scale of these halos is staggering. For a galaxy like the Milky Way, the visible disk might span about 100,000 light-years, but its dark matter halo extends several times farther, maybe 1,000,000 light-years across. Dragonfly 44 is no exception, except that in its case, the halo is almost all there is. The stars are mere decoration on an otherwise invisible structure. What halos are made of? Dark matter halos are composed of, well, dark matter, the mysterious substance that doesn't emit, absorb, or reflect light. The only way we know it's there is by its gravitational pull. It influences how stars orbit, how galaxies rotate, and even how light bends as it passes by, gravitational lensing. Theoretical models suggest that halos formed early in the universe, before galaxies as we know them existed. These halos then acted as cosmic seeds, drawing in gas that could form stars. How we know halos exist. The concept of dark matter halos emerged in the 1970s, when astronomers like Vera Rubin studied rotation curves of spiral galaxies. They found that stars far from the galactic center were moving far faster than could be explained by the visible mass alone. The simplest explanation? There must be an enormous, unseen mass extending far beyond the visible edges of galaxies. Later, galaxy cluster studies, especially work by Fritz Zwicky in the 1930s on the Coma Cluster, the same cluster where Dragonfly 44 lives, reinforced this conclusion. Most of the matter in the universe is invisible. Dragonfly 44's extreme halo. In the case of Dragonfly 44, the dark matter halo is a monster compared to its visible self. It's as if the Milky Way's entire invisible skeleton was left intact, but almost all the flesh, the bright stars and glowing gas, was stripped away or never formed. This makes it an extraordinary test case for studying halo properties. Normally, the luminous matter complicates mass measurements. Stars and gas add their own gravity, muddying the clean profile of the halo. But with Dragonfly 44, you're essentially looking at a nearly naked halo, its dark matter dominance laid bare. Why halos matter for the bigger picture? Dark matter halos aren't just a detail in galaxy formation, they are the framework. If we can understand their shapes, sizes, densities, and interactions, we'll be closer to understanding not only galaxies but also the fundamental nature of dark matter itself. Studying halos like the one in Dragonfly 44 might even tell us whether dark matter is truly cold, moving slowly, as current theory suggests, or if we need to rethink its basic properties. The reason Dragonfly 44 continues to baffle astronomers is that it seems to break one of the fundamental rules of galaxy formation. If you have a massive dark matter halo, you should have lots of stars. That's the standard expectation. In the cosmic playbook, the dark matter halo acts as the stage, gravity pulls in the gas, and then, unless something truly catastrophic happens, the gas cools and forms stars in abundance. But Dragonfly 44 throws that logic right out the window. The mass-to-stars mismatch. Based on its halo mass, roughly half to two-thirds that of the Milky Way, Dragonfly 44 should have a stellar population numbering in the hundreds of billions of stars. Instead, it has barely 1% of the Milky Way stars, maybe a few hundred million at most. In terms of the stellar-to-halo mass ratio, the fraction of a halo's mass tied up in stars, Dragonfly 44 is an outlier of staggering proportions. Most massive galaxies convert at least a few % of their available matter into stars. Dragonfly 44 converts almost nothing. This raises the big question. Why didn't star formation happen here, despite having all the gravitational resources it needed? Environmental puzzles. It's tempting to blame the environment. Dragonfly 44 sits deep in the Coma Cluster, a bustling metropolis of galaxies surrounded by hot, thin plasma known as the intracluster medium. That plasma can strip galaxies of their gas through a process called ram pressure stripping, effectively cutting off their fuel for new stars. But that alone might not be enough to explain D44's extreme faintness. Other galaxies in the same environment still manage to form or retain far more stars. So maybe something about Dragonfly 44's early life was unusual. Perhaps a violent gravitational encounter or an unusually intense burst of supernova feedback blasted away its gas before it could settle into stars. Timing could be everything. Some theories suggest that the timing of a galaxy's gas accretion relative to the universe's early ultraviolet radiation background is crucial. If Dragonfly 44's gas was heated by ultraviolet light from the first stars and galaxies before it could cool, that heat might have prevented it from collapsing into stars. This would essentially freeze the galaxy in a pre-stellar state, leaving the halo full but the interior empty. Why this isn't just a quirk? Dragonfly 44's weirdness isn't just a curiosity, it has broader implications. If a galaxy can be this massive and still fail to form stars, it means our models of star formation efficiency are incomplete. We might be underestimating how often this happens, and how important the suppressive factors are in the galaxy formation recipe. It also suggests that the relationship between halo mass and stellar mass, a key parameter in cosmology, might have more scatter than we thought. That could ripple into our large-scale simulations of the universe, altering predictions about galaxy distribution and brightness. A galaxy that shouldn't exist, but does. The truth is, in most cosmological simulations, a Milky Way scale halo without a luminous galaxy inside is rare, almost to the point of being forbidden. Dragonfly 44 existing in the real universe is a gentle but persistent hint from nature that we're missing part of the story. For all the excitement and study that Dragonfly 44 has attracted since its discovery, the truth is that it remains one of the great unsolved puzzles in modern astronomy. Every time scientists think they're getting closer to understanding it, new uncertainties and alternative possibilities emerge. We know it's big. We know it's faint. We know it's mostly dark matter. But beyond those broad strokes, there's still a galaxy's worth of unanswered questions. The origin story, still a blank page. Perhaps the biggest unknown is how Dragonfly 44 came to be. Did it start life as a normal galaxy that lost most of its stars, or did it always have a low stellar population? Or if it's the result of tidal stripping, a galaxy torn apart by gravitational interactions, we should see certain telltale distortions in its shape, maybe even faint streams of stars trailing away. Some observations hint at this, but others don't. Or if it formed with almost no stars from the beginning, that points to early suppression of star formation, but we don't yet know the mechanism. Was it environmental, Coma Cluster gas stripping, or internal, feedback from early starbursts? Right now, neither explanation fully accounts for the extreme ratio of dark matter to stars. The halo's true shape and mass. Even though initial studies suggested Dragonfly 44's halo is Milky Way scale, later measurements have raised questions about whether those numbers were overestimated. Are we measuring the motions of stars in the right way? Or could there be biases due to the fact that the galaxy is so faint, making it hard to get enough precise velocity data? Or if the halo is smaller than we think, then maybe its star count isn't as extreme an outlier as it seems, though it would still be unusual. At the moment, the mass is still only indirectly inferred from stellar velocities, and further refinements are needed. The missing gas. Another enigma is the complete lack of cold gas. In most galaxies, even if star formation slows, some residual hydrogen remains detectable. Dragonfly 44 appears to be utterly devoid of star-forming material. Or was this gas stripped by the Coma Cluster environment? Or was it blown out by supernovae in an early, brief burst of activity? Or was it never there to begin with? If we could answer the gas question, we'd be closer to reconstructing the galaxy's life story. Stellar population clues. What stars do exist in Dragonfly 44 are faint and old. Studying their chemical composition could reveal whether the galaxy had an early era of enrichment from massive stars. But so far, detailed spectroscopy has been challenging because of the galaxy's extreme faintness. If we could measure the abundance of heavy elements in these stars, it would tell us whether the galaxy went through any substantial periods of star formation in its youth. Dark matter nature. Some researchers have even speculated that unusual galaxies like Dragonfly 44 could help test exotic ideas about dark matter itself. Or if dark matter behaves differently on small scales than in standard cold dark matter theory, that might produce halos that form galaxies in strange ways. There's also a fringe idea that ultra-diffuse galaxies could somehow form in self-interacting dark matter scenarios, where dark matter particles can scatter off one another. We don't yet know whether Dragonfly 44 is simply a rare case within standard physics, or if it's a hint that our physics needs expanding. Is it truly unique? We've found other ultra-diffuse galaxies, but it's still unclear whether Dragonfly 44's combination of size, mass, and faintness is exceptional or just the tip of the iceberg. If future surveys turn up dozens of galaxies like it, that would change the way we interpret it. If it remains a rare outlier, then we have to explain why this galaxy had such an unusual fate. At the heart of it, the mystery of Dragonfly 44 is this: it doesn't fit neatly into any known category of galaxy evolution. Until we know more about its past interactions, its exact mass, and the physics of its star formation, or lack thereof, it will remain one of the strangest members of the cosmic zoo. One of the most fascinating aspects of the Dragonfly 44 story is that it likely would have remained invisible to us without a very particular leap in telescope technology. A leap that wasn't about building bigger telescopes, but about building smarter ones. In astronomy, the instinct is often to go for sheer size. The bigger your telescope's mirror, the more light you can gather, and the fainter the objects you can see. But for ultra-diffuse galaxies like Dragonfly 44, size alone isn't the full solution. These galaxies don't just emit little light, their light is spread out so thinly across the sky that it's almost lost in the glow of the background. Traditional large telescopes, optimized for sharp detail and point-like sources, can actually miss such faint, extended features because of scattered light inside the optics. And that's where the breakthrough came. The Dragonfly telephoto array, a radical rethink. The instrument that spotted Dragonfly 44 wasn't a giant observatory perched on a mountaintop with a single massive mirror. It was something far more unorthodox, the Dragonfly telephoto array. Instead of one big lens, the array uses multiple Canon 400mm telephoto camera lenses. Yes, the kind professional wildlife and sports photographers use, mounted together in a synchronized array. Each lens has a special nano-fabricated coating that drastically reduces internal reflections, which is critical when you're looking for faint, diffuse objects. When light from a dim, spread-out galaxy enters a regular telescope, microscopic imperfections and internal reflections can scatter that light, smearing it into the background noise. The Dragonfly lenses are almost perfectly free of this scattering, allowing astronomers to capture the extremely faint glow of something like Dragonfly 44 without it being washed away. Why this was revolutionary? Before Dragonfly, astronomers knew ultra-diffuse galaxies existed, but they thought they were rare and mostly confined to nearby groups. The problem was that their low surface brightness made them nearly invisible in wide-area surveys. The Dragonfly array's design, multiple small lenses working together like the compound eyes of a dragonfly, allowed it to excel at detecting low-surface brightness objects. It could scan large portions of the sky and spot these ghostly giants in regions where conventional telescopes saw only empty space. The scaling trick. The original Dragonfly array started with just 8 lenses, but it was later expanded to dozens. Each additional lens effectively increases the array's light-gathering power while maintaining its uniquely low-scatter imaging quality. It's a modular system, meaning it can grow in capability without a complete rebuild, a rare flexibility in high-end astronomy. Because it's built from commercially available camera lenses rather than custom-ground astronomical optics, the system is relatively inexpensive compared to large observatories. That allowed researchers like Peter van Dokkum and his colleagues to deploy it quickly and tailor it precisely to their needs. Other technological enablers. Alongside the Dragonfly array itself, other advances made the discovery possible. A sensitive, low-noise CCD cameras that could pick up faint light signals over long exposures without overwhelming them with electronic noise. A automated image stacking and processing software capable of combining hours of exposure time into a single image while preserving faint, extended structures. Image calibration techniques that correct for sky glow, sensor artifacts, and atmospheric interference, all of which can swamp low-surface brightness galaxies. Without these developments, Dragonfly 44's faint smudge would have remained hidden in the static. A paradigm shift in search strategy. Dragonfly 44's discovery was a reminder that different problems in astronomy sometimes need different tools. It's not always about building the next 30-meter telescope. Sometimes it's about using creative engineering to target phenomena that standard equipment struggles to detect. In this case, the leap was realizing that scattered light suppression was more important than raw magnification, and that a carefully assembled array of consumer-grade optics could outperform some of the most advanced telescopes in this particular niche. In the end, Dragonfly 44 owes its place in the astronomical spotlight not only to its bizarre nature, but to the ingenuity of the tools that found it, tools specifically designed to catch sight of the universe's faintest whispers. Astronomers know that Dragonfly 44 is far from giving up all its secrets, and they're determined to squeeze every last photon of information from it. Because it's so faint and so distant, studying it in detail will require a combination of patience, clever strategy, and next-generation instruments. The goal is not just to better understand Dragonfly 44 itself, but also to place it in the broader context of galaxy formation, evolution, and dark matter physics. High-resolution imaging with the Hubble Space Telescope. One of the most immediate steps is to continue observing Dragonfly 44 with the Hubble Space Telescope, HST. While Hubble's strength isn't necessarily in detecting ultra-diffuse galaxies, because it's optimized for sharp detail in brighter targets, it is unmatched when it comes to resolving faint stars individually at great distances. By pushing Hubble's capabilities to their limits, astronomers can map the distribution of Dragonfly 44's brightest stars. Look for evidence of tidal features, faint trails or distortions that could hint at past gravitational encounters. Search for globular clusters in greater numbers and clarity to refine halo mass estimates. These globular clusters act as tracers of gravitational potential, so knowing exactly how many there are and how they move will help narrow down the galaxy's total mass. The James Webb Space Telescope Advantage. The James Webb Space Telescope, JWST, is an even more exciting prospect. While JWST is famous for its deep infrared imaging, that wavelength range is perfect for penetrating cosmic dust and revealing old, faint stars that optical telescopes can miss. For Dragonfly 44, JWST can detect low-mass, ancient stars that make up the bulk of its stellar population. Provide ultra-deep spectra of the galaxy's light, revealing its chemical composition and thus clues about its star formation history. Potentially identify any residual warm dust or unseen stellar populations that might have been missed in visible light studies. Giant ground-based telescopes on the horizon. The next decade will see the arrival of extremely large telescopes, ELTs, such as the 30-meter telescope, TMT, the Giant Magellan Telescope, GMT, the European Extremely Large Telescope, EELT. These observatories will combine massive light-gathering power with advanced adaptive optics, giving them both sensitivity and resolution that dwarf current ground-based facilities. For Dragonfly 44, that means measuring stellar velocities with unprecedented precision, reducing uncertainties in the galaxy's mass, detecting any faint satellite galaxies or tidal debris that might help reconstruct its evolutionary path, directly probing its dark matter halo structure via dynamics of both stars and globular clusters. Radio astronomy and the gas question. One of the great mysteries is Dragonfly 44's apparent lack of cold hydrogen gas. Future observations with ultra-sensitive radio telescopes like the Square Kilometre Array, SKA, or existing giants such as Meerkat will try to detect even trace amounts of neutral hydrogen, HI. If they find none, it will strengthen the case that Dragonfly 44's gas was either stripped early or never accreted in the first place. If they do detect some, it could indicate that the galaxy is in a long-term dormant state, perhaps able to resume star formation under the right conditions. Hunting for more cousins. Another part of the research plan is to look for other galaxies like Dragonfly 44. Surveys using the Dragonfly Telephoto Array, the Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, and even citizen science projects will comb through massive amounts of imaging data to identify additional ultra-diffuse galaxies with extreme dark matter dominance. If more Dragonfly 44 class objects are found, it will help astronomers determine whether it's a rare oddity or part of a broader population, which, in turn, changes how we interpret its origin. Dark matter physics tests. If follow-up observations confirm Dragonfly 44's extreme dark matter fraction, it will become a target for indirect dark matter detection experiments. While these don't involve physically capturing dark matter, they can search for signals like faint gamma-ray emissions that might arise from exotic dark matter particle interactions. Even if no signal is found, the absence of one constrains theoretical models and helps refine our understanding of dark matter properties. In short, Dragonfly 44's future research roadmap is a mix of deep imaging, precision kinematics, environmental study, and population comparison. Every new observation has the potential to either confirm its status as the most extreme known dark matter-dominated galaxy or reveal a twist in the story that forces a rewrite. When you take a step back and view Dragonfly 44 not just as an oddball galaxy but as a data point in humanity's centuries-long quest to understand the cosmos, it becomes more than a curiosity. It becomes a symbol. A ghostly, barely there reminder that the universe we can see is not the universe that exists. A mirror to the invisible universe. Right now, cosmologists estimate that only about 5% of the total energy and matter in the universe is in the form of ordinary matter, the stuff made of protons, neutrons, and electrons that forms stars, planets, and people. The rest is hidden from direct view. 27% is dark matter, unseen but gravitationally active. 68% is dark energy, an even stranger component driving the accelerated expansion of the universe. Most of the time, when we talk about dark matter, we're talking about it as an abstract entity inferred from large-scale gravitational effects, galaxy rotation curves, gravitational lensing, and the cosmic microwave background. But Dragonfly 44 turns that abstraction into a place. It's not just an equation in a cosmology paper. It's an actual galaxy-sized laboratory where dark matter outweighs visible matter 99-1. Why Dragonfly 44 matters to cosmology. Finding a system like Dragonfly 44 is important because it provides a small-scale, real-world testing ground for dark matter theories. If dark matter is made of weakly interacting massive particles, WIMPs, its distribution in Dragonfly 44's halo should match certain simulation predictions. If dark matter instead behaves more like a self-interacting fluid, that would leave different dynamical signatures. If dark matter is something even more exotic, such as ultralight actions, that too might subtly alter the way the galaxy's halo is structured. Ultradark galaxies like this put theoretical physics into a headlock, Either the galaxy's behavior matches predictions, confirming models, or it doesn't, in which case something in our understanding needs to change. A reminder that typical is a dangerous assumption. Astronomy has a bad habit of treating the Milky Way as the template galaxy. But the cosmos is under no obligation to conform to our local neighborhood. Dragonfly 44 is a sharp nudge in the ribs saying, "Don't get comfortable, nature's weirder than you think." Its existence suggests that galaxies can inhabit the extremes of possible structures, huge in size, heavy in mass, but almost starless in appearance. This forces cosmologists to widen the range of permissible outcomes in galaxy formation models, which in turn can ripple through our interpretation of the universe's structure at large scales. The cosmic detective story. In a sense, the hunt for dark matter is the largest detective story in science, a mystery where almost all the suspects are invisible, and the clues are hidden in the way the visible world bends, spins, and moves. Dragonfly 44 is like finding a crime scene where the perpetrator left no fingerprints, just an enormous gravitational footprint. Everything about it points to a presence we can't directly observe, yet which clearly shapes its every feature. Where it fits in the dark matter map. A galaxy rotation curves showed us decades ago that spiral galaxies spin too fast for their visible matter alone to hold them together. A gravitational lensing lets us see invisible mass bending light from background galaxies. Cosmic structure simulations predict vast halos of dark matter around galaxies. Dragonfly 44 adds another layer, a galaxy where dark matter is almost the whole story, stripped of the usual glare of stars. In some ways, it's a purer example of a dark matter halo than the Milky Way, where the baryonic matter, normal matter, complicates the picture. From a human perspective, what's extraordinary is that this discovery happened now, in our time, with our technology. For most of human history, even the idea of other galaxies was unimaginable. Now we're not only mapping them, but finding the ones that hide in plain sight, teaching us lessons about the invisible scaffolding of the cosmos. Dragonfly 44 is a whisper from the hidden universe, a reminder that what we don't see is far more vast than what we do. And in the bigger picture, studying it is part of the same mission that drives all of astrophysics, to peel back the layers of the unknown, one ghostly smudge at a time. When you step outside on a clear night and look up, it feels like you're seeing everything, the stars, the planets, the Milky Way stretching like a river of light across the sky. But the truth is, what you're seeing is the tiniest fraction of reality. It's like staring at the tip of an iceberg and forgetting the mountain of ice below the surface. The vast majority of the universe, its mass, its structure, its deepest truths, is invisible to our eyes. The hidden framework. Dragonfly 44 is more than a galaxy. It's a message. It tells us that what truly shapes the universe isn't the bright, glittering matter we photograph and name. It's the unseen scaffolding of dark matter and dark energy that molds the cosmic web, directs the dance of galaxies, and keeps stars bound together across billions of light-years. This galaxy, nearly as massive as our own but built almost entirely from dark matter, is proof that the forces guiding the cosmos don't need to be visible to be real. It's proof that absence of light doesn't mean absence of influence. The humbling realization. In some ways, Dragonfly 44 should humble us. We humans evolved to trust what we see, a survival instinct that worked fine on the savannah but fails completely on the scale of the cosmos. If we judged reality only by light, Dragonfly 44 might as well not exist. And yet, there it is, a heavyweight in the universe's grand architecture, quietly exerting its pull on nearby galaxies, silently holding itself together against the tug of cosmic tides. It's a reminder that truth is not always luminous, that reality is bigger, darker, and stranger than our senses can comprehend. A universe built in shadows. If most of the universe is dark matter and dark energy, then what we call the visible universe is just the decoration, the light strung along the hidden frame. And just as a building's beauty doesn't reveal the steel beams holding it up, the sparkling galaxies we admire don't reveal the true bulk of the cosmic structure. Dragonfly 44 sits in that darkness, almost camouflaged against the void, showing us what happens when the lights are almost entirely left off. And yet, it's still there, still shaped, still bound, proving that darkness, in the cosmic sense, is not emptiness but substance. Looking forward. Someday, we may discover the exact nature of dark matter. We may build detectors sensitive enough to catch a particle of it in the lab, or develop theories that explain its behavior as naturally as we now explain gravity. When that day comes, Dragonfly 44 will be remembered as one of the early, unmistakable signposts pointing us toward the truth. Until then, it remains a mystery and a monument, a galaxy without a glow, a reminder that in the grand theater of the cosmos, most of the actors perform offstage, unseen, yet shaping the entire performance. And so we end where we began, staring into the darkness, knowing that the darkness is not empty, but alive with the hidden machinery of the universe. Dragonfly 44 is not just an oddity. It's a clue. It's an invitation. It's the cosmos whispering, there's more. Look deeper. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.